All right, so I want you to picture the scene for a second. It's, let's say, January 2026. You step out your front door to grab a coffee. The air is crisp, but the street feels different than it did a few years ago. It's quieter, but somehow much, much busier. You've got a humanoid robot carefully navigating a patch of ice on the sidewalk, balancing a package, and then above you, it's not just one delivery drone, it's a whole swarm of them performing this, intricate synchronized ballet to avoid a power line. And just on the edge of town, there's this grid scale battery facility absorbing a massive sudden spike in solar energy without frying the neighborhood.
It looks like a perfectly well-oiled machine. Or, I mean, it could be magic, depending on how you look at it. But if you're an engineer, you know that what you're actually looking at is a high-wire act, a really dangerous high-speed tightrope walk.
Exactly. And that's what we're digging into today. We have a huge stack of research here. Technical presentations on control theory in 2026, case studies on high-speed maglev trains, reports on EV battery diagnostics, and they all seem to point to this one kind of terrifying reality. The systems we rely on have become so complex that the human brain literally can't visualize how they stay stable anymore.
That is the absolute crux of the problem. We are living through a massive transition in engineering philosophy. It's a showdown, really.
Right?
On one side, you've got the old guard. These are the visual tools engineers have trusted since, the 1930s to literally see stability. And then on the other side, you have the new frontier, these computational solvers that promise to calculate things we can't imagine.
And the sources call it the battle of the spiral versus the solver. Or, if we want to get technical right off the bat, the Nyquist plot versus linear matrix inequalities, LMIs.
Yeah, and it sounds academic, but the stakes are incredibly real. If that robot slips on the ice, it's an annoyance. But if a grid-scale battery controller miscalculates stability, it's a catastrophe. The mission for this deep dive is to figure out, are the old tools just nostalgia? Or does this shiny new black box math have a fatal flaw?
Okay, let's start with the veteran, the old guard,
Yeah.
the Nyquist plot. Now, I know some of our listeners might not have stared at a control chart since college, or maybe never, so paint the picture for us. This isn't a standard XY graph, right?
No, not at all. It's a polar plot. So imagine a graph where you start at the center. As you plot your data, you draw a curve that spirals either outward or inward. This spiral represents the frequency response of your system. So how does the robot react to a slow push versus, say, a high-speed vibration? You plot that whole spectrum as a single curve.
Okay, so we've got a spiral, but there's a specific rule involved, a danger zone.
There is one single point on this entire graph that is the enemy. It is the point -1, -1 on the real axis.
Why -1? Why is that the magic number for everything explodes?
Well, it all comes down to the idea of feedback. Imagine you're pushing a kid on a swing. If you push at the right time, you add energy. Push at the wrong time, you kill the swing. In control theory, a value of -1 means the signal has come back through the loop with the same strength gain of 1, but it's shifted 180 degrees in phase.
Which means your corrective action is actually making the error worse.
Precisely. You push left to correct a drift, but because of the delay, the physics pushes left even harder. That's positive feedback. That creates a runaway oscillation. That is a crash.
So the rule of the spiral is basically don't circle the dot.
In essence, yes. This is something called the principle of the argument from complex analysis. The math gives us a formula. N equals Z minus P.
Okay, wait, I saw that in the notes. N equals Z minus P. Break that down.
It's basically a scorecard. N is what you can see. It's the number of times your spiral encircles that dangerous -1 point.
Yeah.
P is what you started with, the unstable poles that were already in the system before you even turned the controller on. And Z, well, Z is the result. It's the number of unstable poles in the closed-loop system. And you want Z to be 0, always.
So you just look at the map, count the loops, do some quick subtraction, and you know if you're safe.
You know if you're safe, but I think more importantly, you know how safe you are. And this is why engineers love the Nyquist plot. It's all about transparency. The source material uses this great analogy. The Nyquist plot is a map.
Right. If I'm using a GPS, it just tells me turn left in 200 feet. But if I'm looking at a map,
If you're looking at a map, driving on a mountain road, you don't just see the road. You see the cliff edge 3 feet to your right. You see that hairpin turn coming up.
you can see the safety margins.
Exactly. In engineering terms, we call that gain margin and phase margin. You can look at the spiral and say, okay, we're stable, but if the system gets a little sluggish or the friction changes just a tiny bit, that curve is going to cross -1 and we're done. You can feel the physics of it.
That sounds incredibly valuable.
Yeah.
So if this tool is so great and it gives us this, God's eye view of the cliff edge, why are we even talking about replacing it? Why fix what isn't broken?
Because in 2026, the map has become too large to read. We aren't building simple thermostats anymore. We're building systems where everything affects everything else.
This is that explosion of complexity the sources keep mentioning.
Right. Take that humanoid robot on the ice. Doesn't have one motor. It has dozens, and they're all coupled. If the robot moves its left arm to balance a package, that shift in weight affects the right leg, which affects the gyroscope, which affects the head position. This is what we call a MIMO system, multi-input, multi-output.
And I'm guessing you can't just draw a nice, clean 2D spiral for a robot with 50 moving parts.
You can try,
Yeah.
but it gets messy. We'll get to how messy in a minute. But fundamentally, the complexity gap is just too large for a visual tool. You can't eyeball a 100-dimensional vector space. You need a machine to do it for you.
Enter the challenger, the solver, linear matrix inequalities.
This is the heavyweight champion of modern control, LMIs. Instead of looking at a curve on a graph, LMIs look at the energy of the entire system all at once.
I want to get into the math here because the notes highlight a specific formula that seems to be the backbone of this whole new frontier. It's the Lyapunov stability LMI. A transpose P plus PA is less than 0. Now, to the uninitiated, that looks like hieroglyphics. What is that inequality actually asking?
It's actually a really beautiful concept. It's based on Lyapunov theory, which is all about energy. Think of that P in the equation as a way to measure the total air energy in your system. The formula is basically checking the rate of change of that energy.
So it's asking, is the energy in the system growing or is it shrinking?
Exactly. If that whole expression is less than 0, if it's negative, it means the energy of any error is always dissipating. No matter what the robot does, the wobble gets smaller. The system is stable. If it's positive, the energy is growing. That's a crash.
Okay, I think I follow the logic. But this is where the solver part comes in. You don't solve a matrix inequality like that with a pencil and paper, do you?
Oh, absolutely not. For a modern system, these matrices can be massive. You define your system constraints, you set up the inequality, and then you feed it into a software engine, a solver, like MOSEC, Sedumi, or SCS. It's a numerical optimization algorithm.
And the research compares this to a GPS. If Nyquist is the map, the LMI is the GPS.
It is the perfect distinction. With a map, you have to read it, you interpret the cliff, you plan your turn. With the LMI, you just punch in the destination. I want a stable robot. The GPS calculates the route. You don't necessarily know why it decided to turn left on Main Street, but it gets you there.
That sounds, it sounds efficient, but it's also a little bit unnerving, isn't it? It feels like we're just handing the keys over to the machine.
We are. But we get massive benefits in return. First, dimensionality. An LMI doesn't care if you have 2 inputs or 200. It's just a bigger matrix. The computer eats it for breakfast.
And it can juggle different goals, right? It's not just don't crash.
Right. Multi-objective optimization. This is huge in 2026.
Okay.
Let's say you're designing that delivery drone. You want it to be fast, but you also want to save battery life. And you want it to be stable in high winds. Visually trying to balance those 3 things is a nightmare. You'd need, what, a 4-dimensional graph? For an LMI, it's just adding more rows to the inequality.
So you're essentially telling the math, okay, keep energy consumption low, make speed high, and keep that Lyapunov derivative thing negative.
Exactly. And there's one more superpower. Robustness against uncertainty. This is critical. You can tell the solver, hey, I'm only 90% sure about the exact weight of this package. The LMI can find a controller that works for every possible weight within that 10% margin. It optimizes for the worst case scenario.
That sounds unbeatable. If I'm an engineer in 2026, why would I ever look at a spiral graph again? I just hit run on the solver and go get a coffee.
And that is the trap. That is exactly where the new frontier gets dangerous. Because sometimes the GPS drives you right into a lake.
Because it's a black box.
Because it lacks intuition.
Yeah.
The LMI gives you a binary answer. Feasible or infeasible.
Yeah.
It's either here is your controller or just error. It doesn't tell you that you were 0.0001% away from a solution. It doesn't tell you which physical component is causing the problem. It just says no.
It solves the math, but it might be ignoring the physics.
Sometimes, yes. And this is where we have to talk about that complexity gap in the visuals. You mentioned earlier that drawing a spiral for a complex system is hard. It's actually worse than hard. It can be deceptive.
This brings us to the section on generalized Nyquist and the Riemann surface. And I have to admit, looking at the charts in the source material for this, It just looks like a plate of spaghetti dropped on the floor.
That is a very accurate description, actually. When you have a MIMO system, multiple inputs and outputs, you don't get one clean spiral anymore. You get a bundle of them. These are called the characteristic loci.
Characteristic loci. It sounds like a horror movie villain.
It can be a nightmare to read. But the real problem isn't just that there are lots of lines, it's that they switch on you. It's called branch switching.
What does that even mean?
So imagine you're trying to track a blue wire and a red wire in that spaghetti pile. As you change the frequency, the mathematical eigenvalues, the values that define those lines, can actually swap places.
Yeah.
Suddenly the red line twists and becomes the blue line. So if you're trying to count encirclements to see if you're safe, you might miscount because the lines are physically tangling in a way that creates an optical illusion.
So you think you're safe, but you're actually just looking at a mathematical artifact.
Exactly. The visual intuition completely breaks down. It becomes what's called a Riemann surface, a multi-layered surface where you can't tell up from down. A human looks at it and just gets a headache.
But the LMI solver.
The solver just ignores the spaghetti. It doesn't care about the visual mess. It just searches for that mathematical certificate, that P matrix that covers all possibilities. It just cuts right through the knot.
So the solver handles the complexity that blinds the human, but the solver itself is opaque and might miss the physical nuance. It feels like we're stuck between a rock and a hard place here.
Which brings us to the verdict of all this research. The elite engineer of 2026 doesn't pick a side. They don't choose the spiral or the solver. They use a hybrid workflow.
Ah, the notes call it synthesize, verify, validate.
Right. Step 1, synthesis. You use the LMI. You use that heavy computational power to handle the complexity, juggle the 50 motors, and generate a candidate controller. You let the GPS find the route.
You let the computer do the heavy lifting first.
Exactly, but you don't trust it blindly. Step 2, verify. You take that controller the computer gave you, and then you use the generalized Nyquist tools. You look at the spaghetti. But now, because the LMI has already done the optimization, the spaghetti should be much more untangled. You use the visual tool to double-check the robustness margins.
And step 3,
Validation. Real-world physics. And this is where the Nyquist plot makes this surprise comeback in a totally different way. We really need to talk about the EV battery example. This blew my mind a little bit.
the MRI for hardware.
Yes. So, battery chemistry is notoriously hard to model with pure differential equations. It's just messy. You've got ions diffusing through porous materials. There's heat, there's degradation. If you try to build a perfect math model for an LMI, you'll probably fail.
Because the model is always just an approximation of reality.
Right. An LMI model might assume the battery is a perfect little box of energy storage. But if you hook that battery up to an electrochemical impedance spectroscopy machine, which is basically a frequency sweeper, it draws a Nyquist plot of the actual battery.
And the sources mention a tail, a specific little squiggle on the graph.
The Warburg impedance.
Mm.
It's this little 45-degree tail at the very end of the spiral. That specific shape tells you about the diffusion rates deep inside the cell chemistry. An LMI solver working off a theoretical model would never see that. It would optimize for a brand new, perfect theoretical battery.
But the Nyquist plot running on real data is saying, hey, this battery is aging. The diffusion inside is slowing down.
Exactly. It's what we call non-parametric. It doesn't assume a model. It shows you the reality. So here, the spiral isn't a design tool. It's a diagnostic tool.
I want to apply this to that maglev train case study because I think that really cements how these two work together in a super high-stakes environment. We've got a train floating on magnets moving at 500 kilometers an hour.
Extremely high stakes. A maglev suspension is a classic unstable system. If the magnets turn off, the train falls. If they pull too hard, it clamps to the track.
So walk me through the hybrid workflow for that train.
Okay, first the LMI. You need robustness. Let's say sensor number 14 fails mid-ride. You can't have the train crash. You set up an LMI with global constraint satisfaction. It calculates a controller that ensures, mathematically, that if sensor 14 dies, the other magnets instantly compensate to keep the air gap perfectly constant.
So the LMI keeps the train in the air. That's job number 1.
But then, imagine during track testing, the passengers start complaining. The ride feels, I don't know, buzzy. There's this weird vibration at high speeds.
But the LMI says the system is optimal. The energy is minimized.
The LMI minimized the air energy. It's technically stable. But when you pull up the Nyquist plot of the real-time sensor data, you see a spike. A sharp protrusion in the frequency response.
What is it?
It's a structural resonance. The steel track itself is vibrating at a specific frequency, say 400 hertz, that excites the magnets. The LMI smoothed over that bump because mathematically it wasn't big enough to cause a crash. But the Nyquist plot acts as the dashboard warning light. It points right at the problem.
So the LMI keeps the train safe. The Nyquist plot tells you why the ride is bumpy.
That is the perfect summary. One is the autopilot, the other is the diagnostic screen.
It's interesting, this whole shift. In the 20th century, Nyquist was a design tool. You used it to build the thing. Now it seems like it's moved to the other side of the process.
It's been promoted to special investigator. It's used for forensics. When the black box gives you a weird result, or when the real world acts differently than the model, you pull out the spiral to figure out why.
So for the learners listening, or even just the people managing these complex systems, the takeaway isn't learn the new math and just forget the old.
No, absolutely not. The danger in 2026 is becoming a button pusher. Someone who defines the constraints, hits solve, and just assumes the output is absolute truth. That is flying blind.
But conversely, you can't be a Luddite about it.
You can't. If you try to design a swarm of 500 drones using a pencil and paper and a gain margin, you will fail. You need the solver for the complexity, and you need the spiral for the intuition.
It's about fluency in both languages, the language of high-dimensional optimization and the language of visual frequency response.
And knowing when to switch between them, that's what makes you an elite engineer in this new landscape.
You know, this brings up a thought I kind of want to leave our listeners with. We've been talking about robots and trains, but this whole black box versus intuition battle is happening literally everywhere.
Oh, absolutely. AI in finance, AI in logistics, healthcare algorithms.
We're increasingly handing over control to these solvers algorithms that optimize for efficiency, just like that LMI on the maglev train. They keep the system stable, they keep the supply chain moving, the market trading.
But are they smoothing over the bumps?
Exactly. If the LMI smoothed over a vibration that made the ride uncomfortable but was still technically stable, what societal vibrations are our current AI optimization models smoothing over?
That is a very provocative question. We might be optimizing for GDP or efficiency, but totally missing the resonance that causes social friction.
It almost makes you think we need, I don't know, a Nyquist plot for society,
Mm.
a way to visually diagnose the friction that the algorithms miss.
I love that. We need a dashboard for the human element.
Something to mull over next time you see a delivery drone navigate a complex aerial dance. Is it stable? Yes. But is it listening to the wind?
Keep calculating, but always keep looking at the map.
That's it for this deep dive into control theory in 2026. Thanks for listening.